Welcome back. So we are in the next module now, where we'll be talking about the Perceptron learning algorithm. Right. So far we introduced the Perceptron. We saw that the decision boundary that the Perceptron learns is linear, and then we introduced this concept of error, where if the weights are not proper, or if W1, W2 values are not proper, then you will make some errors in dividing the points into the right half spaces, right? So that's what we have learned so far, but we did not talk about how did we get it this W1, W2. We were mainly trying to adjust it by hand. So now we'll look at the Perceptron learning algorithm, which allows us to learn these weights, right? So now, before we do that, let us try to understand that apart from implementing Boolean functions, right? I mean, which does not look very interesting, right? Like, why would you care about Boolean functions? So what is it that the Perceptron can be used for, and what is this connection to the Boolean functions, right? So let's revisit our example, right? So now we are again talking about the case of a binary classifier, and we want to decide whether to watch a movie or not, right? And suppose we are given a list of M movies, all the past movies that we had seen, along with the class label, whether we liked this movie or did not like this movie. Okay? This is based on our past data. So this is just a binary label on all the movies, right? And each movie could be represented by N features. So these features could simply be the inputs which are contributing to the decision. So one input is actor Damon, the other input is the genre thriller, and so on. Right? These are all Boolean inputs that we have, and you could also have some real valued inputs like the IMDb rating, the critics rating of the movie, and so on, right? So all of these inputs are feeding into our Perceptron, and there are also weights associated with them. It's just that we don't know what these weights are, and we want to learn these weights such that once we learn these weights, then for any given new input, it should allow us to make that decision, right? And we should be able to learn these weights in such a way that at least for the given data, and we'll assume that the data is linearly separable, right? So whatever M data points that are given to us, we'll assume that they are linearly separable. That means you can draw a line or a plane or a hyperplane such that all the points for which the output should be positive are in the one half space, and all the points for which the output should be negative are in the other half space, right? So we'll assume that the data is linearly separable. And then in this real classification problem, right, this is not a cooked up problem, this is a real classification problem, we are then interested in learning these weights, right. So that's what we want to use a Perceptron for handling these kind of classification problems, right. Now let's try to look at the Perceptron learning algorithm. So I'll define some notation. So let P be all the inputs for which the label is 1, right. So these are all the positive points that we have been calling in all our discussion earlier, right? And N is all the inputs which have a label 0. So these are all the negative points, right, in our discussion earlier. So now I don't know what the weights are. So what will I do? I'll just initialize the weights randomly, right? And while convergence or while not convergence, till I reach convergence, I'll do something, right? Now, what is the meaning of convergence here? So the meaning of convergence here is that if I reach a point, right, such that my values for W are such that for all the positive points in the data which is given to me, my output is 1, and for all the negative points in the data, my output is 0, right. So in other words, if for all the positive points, summation Wi xi is greater than 0, and for all the negative points, summation Wi xi is less than 0. That means if I have magically reached a configuration where I have learned the Wi's, of course xi's I don't have a control over, right? These are the data that have been given to me. So if all the positive points, this condition is satisfied, and for all the negative points, this condition is satisfied. That means I have to be able to clearly separate my training data, right? And that's what I'll define as convergence, okay? So while not convergence, what will I do? Let's see. So I'll pick a random point from the given set of points. So the given set of points is the union of the positive and the negative points. So I'll just mix up all this and pick a random point from there. I'll call it x, which is the notation we have been using. And now if x belongs to P, so remember that x in itself is x0, x1 all the way up to xn, right. So in our previous example, these are the n decision features that I had. Is actor Matt Damon, is the genre thriller, and so on, and x0 was this constant input which had been set to 1, right. So that is what x, the bold x looks like, it's a vector. And similarly you have these w naughts to wn, right, which is the vector w, okay. Sorry about my handwriting, but I think it's kind of clear from the context what I'm saying, right. So these are the two vectors. So I'm just going to take the weighted sum of wi xi, and if the point was positive and if this weighted sum is less than 0, then you and I understand something bad has happened, right, because if the point was positive, I wanted this weighted sum to be greater than 0. That is what I have said here, right. So something is going wrong. My weights are not the way they should be. So I need to do some correction, okay. And this is the correction I'm going to do. I'm just going to do w is equal to w plus x, okay. I'm not going to say anything more about this at this point. If the point was negative and if my summation was greater than equal to 0, then again I know that something wrong has happened, because for such a point I wanted this summation to be less than 0, right, but that has not happened. So again I need to do some correction, and my correction is going to be w equal to w minus x. Again I am not explaining why this magic formula, right, why am I doing plus x in one case and minus x in one case, and how does this lead me to where I want to go, right. And where do I want to go? I want to go to convergence, where my weights are such that these two conditions are satisfied for all the positive and negative points, right. So how does this ensure that that is what is going to happen? Sorry. Okay. Yeah. So why would this work, right? That's the question that I'm trying to ask, right? It's not very clear to me that why should this work. So to understand this, we'll have to look at a bit of linear algebra and a bit of geometry, right? So let's go there. So we have two vectors w and x, and these are what those vectors look like, w naught up to wn, just as I had written on the previous slide, and x is 1 up to x1, x2, xn, right? And now if I consider the dot product between these two vectors, then this is exactly what I get, right? And this is what the expression that we are seeing on the previous slide. I was taking some decisions based on whether this value was greater than equal to 0 or less than 0, right? So this is the quantity that we were dealing with, and now I'm just telling you, which is obvious, that this quantity is nothing but the dot product between the weight vector and the data vector, right, the data point that I have. So we can thus rewrite the perceptron rule as the following. So y is equal to 1 if the dot product is greater than equal to 0, and y is equal to 0 if the dot product is less than 0. Nothing magical here, the dot product is just equal to this. So I have replaced that cumbersome notation of summation and wi xi by this more compact dot product, right. Now this is where now we need to start digging on. If you are looking at the dot product, right, so now I have gotten hold of some quantity that I can try to explore from a linear algebra perspective, right. What does the dot product mean? And then try to come up with some explanation for why should the algorithm work, or what is it why is it making sense, right. So we are interested in finding this line w transpose x equal to 0, which divides the input into two halves, right. That we have already understood. We want to learn these w's, right. So now any point which lies on this line, it will satisfy this equation, right. I mean, that's a trivial statement to make, right. So if you have the line y is equal to mx plus c, right, then any point x comma y which lies on this line will satisfy this equation. That's the same thing I am saying. It's just that now my way of writing equations is slightly different. I am calling this as x1, I am calling this as x2, and maybe I am calling this as w naught, right. So that's the only notation change that I have. So I have w1 x1, right, plus w2 x2 plus w naught equal to 0. So this is the equation of a line which is analogous to this equation that I have. And all I am saying is that any point which lies on this line satisfies this equation, right? And that's a trivial statement to make. Now what can you tell us about the angle between any such point, right, and the vector w? So first of all, we have to again realize that both x and w are vectors, and that's precisely what is defined here. So now I can ask this question. If I am saying that any point which lies on this line satisfies this equation, so then if it satisfies this equation, what can you say about the angle between the point and the vector w? If it satisfies the equation w transpose equal to 0, that means these two vectors are orthogonal. We know that from linear algebra. So the angle is going to be 90 degrees, right. and because we know that cos of the angle is equal to this formula, and if W transpose X is 0, so the cos of the angle would be 0 and the angle would be 90 degrees, right. So, this is slowly we have now started moving into the territory of geometry and linear algebra, right. So, now we know that if the point lies on the line, then the angle is 90 degree with the weight vector, okay. Now, let us go ahead, right. So, if the vector W, right, if it is perpendicular to every point on the line, then it just simply means that it is perpendicular to the line, right. So, if this is the line W transpose X equal to 0, then my weight vector is going to be perpendicular to that. So, nothing great again, right. Now, let us see some points which lie in the positive half space of this line, right. So, this is my line, and I am going to look at the points which lie in the positive half space. What is the positive half space? It means that W transpose X should be greater than 0, right. So, here are these points. Now, my question is, what would be the angle between these points and the weight vector W? Without knowing anything, just that by looking at the picture, you should be able to tell me that this angle would be less than 90 degrees, right. It is obvious from the picture, right. And why is, let's see if I want to answer this now, and now let us look at some points which lie in the negative half space, right, which are these red points. What would be, and by definition, if it is in the negative half space, then W transpose X is less than 0. So, what would be the angle between these points and the weight vector? Again, just by looking at the picture, it is clear that the angle should be greater than 90 degrees, right. So, if I consider this point here, this angle is clearly greater than 90 degrees, because I mean, you know, it is greater than 90 degrees, okay. So, that also is clear now, right. So, now let us try to relate the expression that we had with this geometry, right. This simply follows from the formula. So, you had the cos alpha is, the formula for that is W transpose X divided by the norm of W and norm of X, right. So, if W transpose X is greater than 0, right, that means cos alpha is greater than 0. If cos alpha is greater than 0, that means alpha is going to be less than 90 degrees, right. So, that is what it follows from, because the points lying in the positive half space satisfy this expression, this inequality. That is why the angle is going to be less than 90 degrees, and because the points lying in the negative half space satisfy this inequality, that is why the angle is going to be less than 90 degrees. So, you just do not know this pictorially now, you also know that it follows from this inequality, right. So, all positive points will have a acute angle, all positive negative points will have an angle which is greater than 90 degrees, right. So, now with this explanation in mind, let us revisit the algorithm and let us try to see what is happening there, right. So, what was I doing? If I had a positive point on which I was making an error, then I was changing the weight vector by adding the point to the weight vector, right. That is what is happening. If I had a positive point on which I was making an error, then I was changing the weight vector by adding the point to it, right. So, let us see what happens by that, right. So, if X is belonging to P and if W transpose X is less than 0, that is what this expression means, right. Then it means that the angle between this X and the current W is greater than 90 degrees, right. But that is not what I wanted. I wanted this angle to be less than 90 degrees. So, now what is it, what should my goal be if I am in this situation, that my W and X are such that the angle is greater than 90 degrees and I want it to be less than 90 degrees. So, I should try to adjust the W at least such that whatever is the current angle, that angle should decrease. It may not become less than 90 degrees at one shot, but at least it should decrease from where it is currently, because right now I am in a bad situation, right? That is what I should do. So, let us see what happens if we do this update. So, this is the update that we do. Our goal was to want it to be less than 90 degrees. We somehow ignored that goal and went ahead and said, okay, let me do this. So, what I need to convince you is that whether this is in line with my goal or not, right. So, if my new W is W plus X, so let me now check what my new angle would be, right. My new angle would be proportional to this, right. Now, let me just substitute the value of W new, it is W plus X, okay. Let me just open up the bracket, W transpose X plus X transpose X. W transpose X is cos alpha, right. So, cos alpha new is actually greater than cos alpha. That means alpha new would be less than alpha. That is what I wanted. Whatever was my current alpha, I wanted my new alpha to be less than that. Eventually, I want to get it to less than 90 degrees, but I may not be able to do it at one shot. So, I will slowly try to make it less than that, right. So, that is what has happened here, Okay, there is some hidden stuff here, right? So, I have conveniently used this proportional sign and ignored the denominator and all, which simplifies the calculation for me and it makes it easier for me to show the intuition. If you add the denominator and all, you will kind of realize that it's a bit more trickier calculation, but the idea is just to give you the intuition, right? So, you understand now that with this update, the alpha actually becomes less than what it was currently, and that's exactly what I wanted, right? Let's look at the other case. If x was a negative point and if I was making an error, right? So, if W transpose x was greater than or equal to 0, that means the current angle is less than 90 degrees. But what do I want? I want it to be greater than 90 degrees, right? So, if I look at it at one step at a time, whatever is the current angle, I want the new angle to be greater than this angle, right? So, let's see if that happens if I do W nu equal to W minus x. The same explanation, cos alpha nu is going to be this. I'll substitute the value, I'll replace, open up the bracket, and now you can see that cos alpha nu is actually less than cos alpha, right? If cos alpha nu is less than cos alpha, that means alpha nu is greater than alpha, right? And that's what I wanted. My current angle was less than 90 degrees, which was not acceptable to me. I wanted it to be more than 90 degrees. So, this step has at least ensured that my new angle is greater than my current angle. And I'll maybe slowly keep doing this and move towards convergence, right? Slowly I'll keep changing this angle iteratively, right? Because I'm going to do this iteratively. It's not that once I pick up a point and I adjust my W, I'll never revisit that point, right? I'll keep doing this till I reach convergence. That will, I keep picking these points again and again cyclically, right? So, at some point I'll keep changing it and then eventually it will cross 90 degrees, right? So, that's the intuition that we have here, right? And that's why that update makes sense. Still a bit more to it, right? I mean, some of you should start thinking, oh wait, when I see a positive point, I make an error, I change the W so that this angle becomes something. Now, if the next step, if I take a negative point, I make an error, I again change the W. Now, how does this ensure that I don't keep toggling like this, right? For a positive point, I change the W so that the angle became less than what it was earlier. For a negative point, I change the W so that the angle became greater than what it was earlier. But if I keep doing this, then what if I just keep toggling and never reach convergence, right? So, what's the proof of convergence? That we have not done that. I have just explained you the intuition behind these steps. Why do these steps make sense? I still need to explain whether this algorithm will converge or not. We'll get to that later, right? So, now let's try to see this algorithm on a toy data set, right? So, to convince ourselves that the explanation was indeed correct, right? So, we initialize W to a random value. So this is what my W is, okay, I will just initialize it randomly and you will observe that currently my W is exactly opposite of what it should be, right. It has a angle less than 90 degrees with all the negative points and an angle greater than 90 degrees with all the positive points, right. This is exactly opposite of what I wanted, right. Yes, W transpose x equal to 0 is the equation of the, yeah. So, I'm not happy with the situation, right, because my W is clearly not what I want it to be. So, let's just run the Perceptron algorithm, right. So, what will I do? What does the algorithm do? It picks up a point randomly from the union of p comma n, right. So, let's say I randomly picked up a point and the point was P1, okay, and my condition is not satisfied. So, W transpose x or the dot product between W and x is less than 0. Right, whereas I want it to be greater than equal to 0. So, I will have to apply a correction, right. So, now I am going to apply the correction W is equal to W plus x, where x is nothing but the point P1, okay. So, if I apply this correction, let us see what happens. So, you can see that my W has changed, right, and you can see as I was expecting, the new angle between W and P1 is now less than the older angle, right. So, this greedy step has worked in doing whatever it was set to do. Right. So, it has reduced the angle. Now, let me do it again, right. So, now again randomly pick a point and say this time the point that I pick is P2, okay. So, I will compute the angle between, I will just compute the dot product W transpose x and again I am seeing that the, I already did the correction, this is where I was. So, I picked the point P2 and again you can see with this W, the angle is still greater than 0, right, greater than 90 degrees. So I don't want that. So I'll have to apply a correction here also. What will the correction be? I'll add P2 to W and I'll get a new W. So this is what my new W looks like. And you can again see that the angle has decreased. In fact, here it has already become less than 90, but I don't care about it. All I care about is the angle has decreased. Now let me pick up another point. And this time maybe I picked up N1, right? And now with N1, I again need to apply correction because you can see that the angle is actually quite small, right? It's, forget about greater than 90, it's actually quite small. So I need to again change it and my adjustment would be W into W is equal to W minus X. And when I do that, I get this new W, right? And I can again see that the angle has increased, okay? Now let me do, again pick a random point and say it was N3. No correction is needed because you can see that N3 is already making an obtuse angle with the weight vector, right? So no correction is needed because the condition is already satisfied. Again I pick up a random point, it's N2. So again N2 is already safe because the angle seems to be greater than 90 degrees, so I don't need to do any correction. Now I pick up the point P3 and I need to make a correction because with P3 I can see that the angle is greater than 90 degrees. So I'll do the same correction and this is what my new W looks like, okay. Now let me pick up the point, another point randomly and say it's P2. No correction is needed because you can see visually that the angle is less than 92. Again I pick up N1, no correction is needed, the angle is greater than 90 degrees. Again I pick up N3, no correction is needed. I keep doing this, I keep cycling through the data and I now know that I have reached convergence. I'll cycle through the entire data once and I'll see that no correction is needed. That means I have reached convergence, and that's what convergence means. I'll just cycle through the entire data and if I don't have to change my W, that means all my positive points have the right angle with W, right angle meaning the correct angle with W, and all my negative points also have the correct angle with W, so I don't need to change anything, right? So that's how it has changed. Now the question whether I could have just kept toggling, so I picked up N2, I had to make a change. If I picked P1, I had to make a change. At the beginning you saw we were making changes. So what if these changes were counterproductive, right? It just moved somewhere, then again it moved somewhere and it ended up changing the angle with the original point which I had corrected in the last step, right? So that is not yet clear, right? Whether the algorithm will keep toggling or whether it will converge, that is not clear. That's something that we need to see.